GDS Lab is for the control and data acquisition of a whole range of laboratory test equipment, from running a simple odometer or bank of odometers to a stress path system or a complete dynamic hollow cylinder system or variable direction simple shear even. All systems use the same software, with some simply utilizing more features than others. The main USP of GDS Lab is the way that hardware can be selected and set up in whatever way you want it connected. GDS Lab even allows for equipment from other manufacturers to be configured, thus allowing GDS Lab to form the software base for the upgrade of existing equipment. We will explore this in a bit. Here we can see the GDS Lab kernel has started. Click here to begin signifies that we need to create a station before we can continue. Creating a station involves choosing an initialization file, a text file basically that specifies exactly what equipment we want connected to GDS Lab. For example, here, if I choose this file I have made called GDS AOS, this will create a station based on a single GDS automated odometer system. If I wanted to connect this, I go to the object display, click on the device, and it's very easy to connect. I would simply press select controller. But as I haven't got one of these connected, I'm going to move on to something that I have got connected. The flexibility of GDS Lab means that if I have a GDS Lab driver for a device, I can set that device up within my station. So I'm just going to remove that station. And here, I want to highlight one of the real advantages of GDS Lab, in that if I choose this triaxial station that I know contains an ELE load frame, if I go to the object display, we can see a completely different system has been set up, which includes an ELE tri-test load frame. The ELE load frame is being used in conjunction with two GDS version 1 standard controllers, which are on the serial port, and a GDS data acquisition device here called a serial pad. This shows exactly how we can use the equipment from other manufacturers just as easily as those from GDS. This is perfect for upgrading your system. If, for example, you already had an ELE load frame with a triaxial cell, you could purchase software, two pressure controllers, and a logger from GDS, in effect around half of a system essentially, and create a fully automated stress path capable system. This station also has 3 channels configured, but in fact I can configure all of the available channels. The flexibility of GDS Lab means that from a single device it could be shared between other stations. Here, channels 4, 5 and 6, for example, I'm only using 0, 1, 2. 4, 5 and 6 could be used on a second triaxial station or logging from a hanging weight odometer, just to give 2 examples. The station I want to demonstrate, however, is this one. If I just remove the station and create this one, it's a typical GDS triaxial automated system. This one we will see has 2 version 2 standard controllers, which are both on USB, and a version 2 50 kilonewton load frame. Here it comes. Also has the same 8-channel data acquisition device as the other system. Now I'm going to show how we actually set this up by clicking on each of the devices. We can see how easy it is. I know that this device is serial. COM port 5 I know is the COM port on my computer, and 4800 is correct. So in theory now I should be able to take a reading. Perfect. Now what I can also see is, let's just do a read now, and you will see that none of the other devices are actually connected. Error, error. So if I get back out of that, if I click on this controller, it will open a window and I can select the device. Now I know that this one, serial number 12636, I have connected as my cell pressure controller. I click on the back pressure controller and select it. I know that I have 20055 as my back pressure controller. And now for the load frame, just click on it and it's automatically selected actually. So 19364, I can check on the back of my load frame. Yes, that's the right one. Now if I select read, it should read from all the devices. So it really is as simple as that. So just to show, if I close down the software again, reopen, I'm going to Cyclic here to begin. This STD TAS, I'm going to say to always start with this file, because let's face it, we don't actually change our systems very often. So whenever I start the software in the future, it will start with this file, and all of the settings will be remembered so that immediately off I go. So that was very, very simple to set up. Now we need to set up transducers. Now this is particularly easy. Now for the cell pressure controller, for example, all of the settings are recovered directly from the device. So there's no calibration factor required, so it's defaulted to 1 because the calibration is in the actual device. But for this data acquisition device here, we need to set up the calibration details for the load cell in this case. So all of these elements have been manually put in by myself a moment ago. Set the soft 0 back to 0. Essentially we've got millivolts, which we can't change because the software knows that this data acquisition device is returning millivolts. But we need to put in the factor such that the millivolts are converted to engineering units. I know that the full scale of this load cell, actually it's 19.6, so I'm going to change this to 20 millivolts to represent the full scale, which will give it the best resolution. When I click away, it will set the full scale on the device to 20 millivolts, which is one of the ranges on the serial pad. I can choose the number of decimal places. In this case, I do think 3, so we read to 1 Newton is perfect, and we know that kilonewtons is what we want. So if I press read, you can see we've got a reading. I'm going to do what we call a sanity check. Push up on this load cell and make sure we are actually getting a reading. Yes. Okay, so we're getting a reading, which gives me a great deal of confidence that we set that up. Okay. And I'm going to set that to 0. So you can see that shows you how to set up your transducers, and we get a really nice view of all of the information coming from our devices. The eye icon here, you can see, represents all of the transducers, all the raw values that are going to be read during the test. Now these are set up in the ini file, so if we wanted to add additional transducers to this serial pad, it would be very simple in the ini file. I can toggle between the eyes and the CP, which is control parameter, and you can see everything that we can control. Well, if I want, I can display them both on the same screen and read them. Just make that a tiny bit smaller. So as an example, for this cell pressure controller, it's currently reading 23 kPa. If I want to increase that to say 50 kPa for the test, press set target, and off it goes. You saw the cell volume change slightly, and it's maintaining 50 kPa. So you can see that's very easy to manually set up the test, and it just helps having pictures of the devices on screen, which gives us a lot better chance of identifying each of the devices. So if I exit from that, we're now back to the main test program. Assuming we have all of the test equipment set up correctly and we know that it's working, we can go onto the test plan and create a triaxial test. So if I first choose data save, we can choose a data file. We can either choose a sort of more traditional way of saving data in a single directory, so we give it one file name and off we go, or the GDS Lab project structure is saves in a way that uses GDS Lab reports, which is a program that sucks the data up for immediate presentation to British standards. So So if you're a commercial laboratory, you might be interested in looking at that, and it exports it straight to an Excel spreadsheet for you. But we'll choose single directory in this occasion, and I'm going to choose to save every 5 seconds actually. Here we've got a choice of some backward compatible, very old GDS formats. Maybe if you're running a piece of software called GDS TAS or STD-TTS, and you've got spreadsheets set up, you can save it in that original format. You can choose to save linearly, 5 seconds is what I've chosen here, or you can choose to save square root, log, or even a custom time file if you say it's pretty standard and you want to save it at particular points in time. You can create a custom time file. And here I'm going to choose to save the calculated data as well, so that we can see all the actual stresses, P's and Q's, etc. Next, let's give it a file name. I'm going to go for the traditional own name with a 1. There we go. And we've got a tick there to show that we've set up the data file. Next, I need to choose a sample. Now, we have a number of samples here, and I'm going to run an unconsolidated, undrained test. So I'm going to choose UU, which will be input data, essentially based on a BS 1377 UU test. Of course, there are a whole list of specimens there from shear box, odometers, etc. Is this the first test on a new specimen? I'm going to say yes, because it is. And that will ensure that back volume changes and things get set to 0. Is the specimen docked? I'm going to say yes. Makes things a little bit easier for us. And what that does is that then sets the displacement transducer to 0 at the start of the test. So we can enter whatever we want. File demo, and we enter in here the height of the sample, diameter, etc. That's 50. Upthrust is the ram diameter. If we have an external load cell, we need to put in a ram diameter so that we can compensate for the upthrust of the cell pressure acting on the ram. But here I have an internal submersible load cell which compensates for the change in cell pressure. Highly recommended piece of kit, and I'm not going to apply membrane correction. So now I'm going to think of adding a test. The test modules are vast and varied, to say the least. Here you can see we've got dynamic loading, K0, permeability tests. Now it's because I've got enabled on my dongle pretty much every GDS Lab test module going. But what we're going to choose, just as a demonstration, is standard triaxial. So if I create a new test, you can see that we've got just the data that's required for a shearing stage of a test. So I'm going to choose unconsolidated, undrained. I'm going to choose a cell pressure just to be different, slightly higher than what we have currently in the system. Remember I set 50 earlier. And I'm going to choose a very fast velocity, 1 millimeter per minute, which is unrealistic for any sort of soil test, but I've actually got a bit of rubber here just so that we can see the test running. I'm going to choose next. We have various options in all of the test modules. One here for automatic docking, set the displacement transducer to 0. Yeah, I think I'll do that. And termination conditions. Here we can terminate on 5 kilonewtons maximum, maybe a certain time, maybe 20% strain, maybe a minimum maximum stress, maximum deviated stress, and there's also some advanced ones here, which there's a minimum axial stress, maybe if we're going into extension, for example. Once we've set up all of our termination conditions, some of these being safety limits at the end of the day, we can add that to the test list. And if I look at the test list, you will see we have one test stage there, which is the one we've just set up. One thing I didn't go over there, when it gets to the end of that test stage, for example at 5 kilonewtons or 30 minutes, whatever we choose, we can choose to go to the next stage automatically or wait for user interaction. what this essentially allows us to do is to set up a whole load of stages, maybe 5, 10, 20 stages, however many you want. And by carefully deciding between the start and the end parameters, you can set up multi-stage testing. You can do a number of tests, a number of stress paths interconnected, essentially run the test overnight or during the day without having to come back and attend it. Or the other option that you saw there, which is wait for user interaction, is in case you maybe want to see the results of that stage before you move on to the next stage. Anyway, I've just set up the one stage at the moment. Go to test, and then I'm going to say start test. Load frame should start running, which I can see it has. Set the displacement to 0, and on the screen, if I choose data options, we can choose all of the data we see on the right hand side of the screen, so like live updates, including calculated parameters. I'm going to choose deviated stress and axial stress, just as an example. You'll see they will appear there. And we have a similar sort of selection for graphs. So graph 2 has already been set up for time this stage against load cell. If I wanted to, I could change that to maybe axial displacement against load cell, which axial displacement I haven't set up correctly. I'll come back to that. Let's go back to time this stage. I haven't actually got my external displacement transducer connected, so we'll just have to look at time this stage against load cell for now. Okay, what I'm going to do is I'm going to leave that to run for a while, and we'll come back in a few minutes when that's gone just a little bit further. Okay, the test has just been running for a few minutes. I'm going to try and preempt the ending of a test stage, but at the same time I'm going to carry on and run another test. So let's give it a maximum value actually of say 0.6 kilonewtons before it actually got there. And if I say go to test, when this reaches 0.6 we should see that the test will stop. No further stages. Let me set up another stage. I'm going to do, I'm going to run an advanced loading test. Let's see if we can do something with a very, very basic system that's just a little bit special. Cell pressure will keep constant. Let's just up it to 65. Back pressure will keep constant at 60. Now, what the test module I've started here is the advanced loading module, which is very, very generic test module for pretty much doing anything you want to do, really. With it treats each axis as a separate axis, so you can choose whether you want to do, for example, here with the cell pressure, constant ramp sinusoidal on the cell pressure. In fact, yeah, let's do that. Let's do a sinusoidal on the cell pressure. Let's keep the data at 60, and we might want to do a period of say 4 minutes and an amplitude of 40 kPa. So we're doing cyclic loading essentially on the cell pressure, which is a bit special considering it's essentially a standard standard triaxial system. And on axial stress, on the axial displacement, I'm going to leave that as halt. So yeah, okay, all we're going to do is cycle the cell pressure. Again, we've got end of stage options, but I'm just going to run this, go to test, next stage, and if we look at our cell pressure and our back pressure raised up to 60, and our cell pressure is off on its little 4-minute period cycle. So what I'm going to do is pause the test, and I'll come back to it in a few minutes when it's done something a bit more interesting. Thank you. Okay, the test has been running for 5 odd minutes in this particular stage, and you can see we've got a nice sinusoidal wave on the cell pressure. What I'm going to do is pause the test. Now that would continue indefinitely, so a nice radial stress cycle. But you know, I said that we didn't have a displacement transducer, I've just set one up in the 5 minutes that test was running on the load frame. So now we have here frame displacement currently on 0. Because we have frame displacement now, we're going to be able to control it, because it's actually quite a special feature, I would say, because essentially this is a standard triaxial setup, which could be with any velocity controlled load frame from any manufacturer. So a very, very basic staple piece of equipment that most laboratories have, that they only ever use by walking up to it, pressing start in a particular velocity, and maybe taking the details down on a clipboard. But by setting it up as a GDS task system, we can do something really quite special, and even go as far as cyclic loading, either stress control or strain control. So I just want to demonstrate that, because I think that's really quite a cool thing to do. So I'm going to keep cell pressure at 60, back pressure at 50, just so that it's there. And I'm going to do sinusoidal on the axial displacement. I'm going to keep the datum of 0, period of about 3 or 4 minutes, because it's a static velocity controlled load frame, is about as fast as we can go, and an amplitude of, let's go for something a bit weird, 0.85 millimeters. And let's see how it does. We're not going to have any termination conditions. We want the cycles just to run and run and run. I'm going to change save interval to 5 seconds though, so we get a little bit more data. Start test. Now let's set up our graphs. Let's go to graph 3, and we want to see time since the start of the test, or the start of the stage, because it's the start of the stage is the start of the test. And I want to look at axial displacement, and let's have nothing on the second axis. So off it goes, and this is a velocity controlled cyclic test. So what I'll do is I'll leave that running for a few minutes, and we'll come back to it in a moment, and hopefully we'll see what the system's done and what it's capable of. Hi, and back to the test. We can see we've done 3 nice displacement controlled cycles. Zoom into any pair of these, and you can see we've got really nice shape. So that's really quite special, I think. So any questions, just contact us, www.gdsinstruments.com. My name's Karl Snelling. I'm Managing Director of GDS Instruments. You're very welcome to contact me directly, or support@gdsinstruments.com. Be in touch. Thank you very much. Cheers. Bye.